mind. Some of you are working on stars, some of you are working on gamma ray bursts, some of you are working on different things. And so all of the concepts may be applicable to different areas of research going on at the Center for Astrophysics here at Harvard Smithsonian. So are there any comments or questions? Cameron, glad to hear from you. Oh, he's a real expert on some of this.
So one of the comments that we got into a discussion with especially the classifiers is, and maybe you just have some general comments, is that all of these methods that we ran through real quick have different, make different assumptions and have, different problems, right? SVM, does linear and, but it maps nonlinear spaces by going to a higher dimensional space, right? And some of those have implications for the real science we're doing, adding complexity or other things. And so you often have to know the right, what you're looking at or what you're doing. For example, one of my common complaints on neural nets is that they can do these nonlinear mappings, but it's very hard to figure out what happens when you put new data in because there's no intuition that you can get by looking at the node weights that it builds internally. And so there's different things that you can get out of this. Like, for example, some of the simple methods like decision trees give you these planar cuts that you can then look at and go, oh, that makes sense or that doesn't, right? You can map that back into something you understand. I just figured if you have some comments on what the advantages or disadvantages of some of these methods are, or how to use them, or the importance of doing that.
Frankly, my comments are almost identical to yours, Cameron McBride. So I think you really got it down pat. Some of them are easily interpreted. A regression, you've chosen a response variable. You know what that is. Star formation efficiency in some galaxy or something. And it is a function of things that you know and measure. And so your result is going to be easily understood. But even something like a principal component analysis, which is sort of like a regression, might intertwine them into several components, each of them with all the variables sort of loaded in different ways. And it becomes a little more difficult to interpret even something like principal components, which is extremely old and simple. And then absolutely, if you have a neural net, that's one of the reasons why it's a little irritating that neural nets got a bigger hold in the community than CART, just by coincidence, interest of a few pioneers. Because, in fact, it's almost impossible to interpret the nodes of neural nets. And they'll all change as you change the layers and the topology of the network. And you might want to change it to improve the performance, but you have no idea what it means. And so neural nets are notorious for being opaque. Okay, but whereas CART decision trees are very simple. We're all used to saying, oh, G minus R is less than 0.04. Okay, yeah, that's a reasonable idea. Okay, all it's doing is quantifying a very intuitive procedure. So my answer is that, Cameron, you've done the right thing. You stopped exactly by describing that. There's no conclusion to reach. Astronomers can choose methods that are intuitive or choose methods that have high performance. Hopefully you get one that's both. My personal opinion is don't choose abstractly one thing in advance and go do it and then publish. Because there's a worry that your science depends sensitively on your chosen methodology. I would go and play your saxophone, fiddle around, what's it called, jamming like jazz, okay? Go into R and try things out, take only 10,000 points and just sort of fiddle around a bit, Get a sense of what different methodologies do for your particular problem. I don't think even a statistician or an engineer could tell you what is right for your problem. They explore also. I think they could say, oh, well, your problem is complex in this way. Definitely don't do such and such. You're just hopeless. But beyond that, it's not obvious. I think it's worthwhile to know that in terms of supervised classification, that random forests, the modern version of classification of regression trees, CART, and support vector machines, the modern version of LDA, have basically won the popularity race of being very effective. So it's not a coincidence that when a high-quality, cross-disciplinary astrostatistics group at University of California, Berkeley, under Joshua Bloom, with Joey Richards, who's now a statistician who's left the group and has gone to industry, I think. Oh, that's all too typical. They were classifying irregularly sampled time series in preparation for LSST and making training samples of all the weird periodic variables and all the weird type of things. And they ended up testing about 10 or 15 different methods and using similar cross-validation type performance indicators. And they end up saying support vector machines is the best or random forest is the best. It's not a big surprise. The group in Leuven, Belgium, who's doing it for Gaia, similar results. So if you don't really want to spend a lot of time exploring, try random forest and support vector machines. It's not a coincidence they have more than 1 million Google hits. Yeah, they're very powerful and multi-talented methods. But there could be something simpler for you, for your problem. And one more time for another comment or question. Regression, density estimation, classification, clustering.
I was going to ask the question that you refused to answer before, which is, what do you do when you find that your numbers don't match up? So what would you do to solve the problem that you refuse to solve?
You mean, sorry. Oh, well, I see. Oh, I would go look at the vectors.
Okay.
And find out why one of them had one more element than the other. Right. See if there was a zero. Go back and read my code and figure out why it happened. Maybe it was produced by one of the programs. I have to do STR structure of all these complicated output lists and figure out what came out of some intermediate program, because essentially I'm using them like black boxes and maybe I didn't understand what it produced. And I debug. I'd have to figure out. I mean, the advantage of debugging is it slows you down. It makes you think a little more about what you're doing. So it is an advantage to debugging, to having mistakes that you debug. Yes, sir.
I have a very stupid question, but so far we've been cutting and pasting from a text file.
Yes.
Presumably there's some form of idea like scripts that one can write and read in and run in R, or
well, of course, when you write your own script, you save it on your disk and you use source. Source will bring in any script that you have. So another R expert. Anything besides source? I forgot. Load. Load. You can save large files and save environments with load and save. History saves and loads commands that you type in, but if you're wandering around, they're all confused, but you can save good ones. These are some of the, okay. Then there's entire GUI'd environments for being much more gracious in R scripting than I'm doing here. The most popular one is called RStudio. It's used by industry, it's used by students, and there's no reason why we don't use it. It sets up several frames on your screen where you script over there, and your console is there, and your graphics is there, and it's sort of a pleasanter environment for R development, RStudio, and there's several others as well. R has been GUI'd up to even look like Windows, which is R Commander, which doesn't appeal to us. We've never been Windows pull-down menus, but there's a whole world of people who only know pull-down menus, and so they needed to make R look like that for a while. That took a lot of computer science to do that. That was hard, apparently. So there's so much associated with R that almost any need you have of this type has been addressed often multiple times, but that doesn't mean it's easy to find it. And it doesn't even mean it's worthwhile learning it. It's not always perfect.
So can I ask a different question?
Please.
Yesterday you made a comment that fitting power laws, binning the data was the worst thing to do.
Yes.
And so could you comment?
No, I'll do that at 3 o'clock today. It's a common mistake, so that's what a common mistake talk. Yes, Dr. Kellogg.
They're like groups Are there like special interest groups, like somebody wants to analyze Chandra data, a spectra or something, then they have some sort of a place that they'll...
Okay, at the moment for R, no, almost nobody. I'm a roving educator of an unknown code to most astronomers, right? I think I asked at the beginning, how many of you know R? And there was only a smattering. And this is CFA. This is a great center of astrophysics and even of astrostatistics.
Associate R with business, and so they don't get involved.
Whatever. It's actually associated with the statistical academic community. Those are the people who created R, and they're the ones who are fully committed and glommed into R. They do all of their development in R. So it's statisticians who do R. And industry... Okay, what can I say? The sociology of it. Now, there's a vast amount of R blogs, R question forums. There's an enormous amount of resources out there. They're a little notorious for being a little testy. You get into r-bloggers.com and you ask a question, and they'll say, you didn't read the help file that I wrote 20 years ago. So they're not always polite, but they will answer your questions. I've tried this 3 ways, and how do I do it? And it's like any complicated program, there are tricks, and some of them require the real experts, of which there are a couple dozen. Absolutely. At the base of R. They're our core team. And they read the blogs and they answer the questions. And then there's another layer of very good experts. And in all of astronomy is Gus Muncher. Okay, there's a couple astronomers who do a lot of R. Cameron, do you do a lot of R?
No, I do some.
Okay. I do medium, not very good. I'm more of a teacher. But we should get experts, just like we've got whizzes at Python. And we should get some whizzes at R. Yes, but he was a statistician, Joey Richards.
No, I'm talking about Joey Richards, who's an astronomer.
Oh, yes.
These redshifts of galaxies and such.
Okay, there's 2 Joey Richards. Okay, I didn't know that the other Joey Richards also likes R. I'm now thoroughly confused. Okay. Oh, well, thank you. Maybe you should tell me about this. We could put it on ASAIP. He should be introduced to ASAIP. That's the place to do it. So I think, Ed, to your really answer is that R is so new to our community that the ASAIP, this portal, is a place where people can start talking. And the astro.r Facebook group of Aaron Rebatham. Those are the places where these discussions are beginning. But they have not matured at all. And we don't really have Astro R repositories. And there's about a dozen CRAN packages by astronomers for astronomers. And I'd say 8 of the 12 were written in 2013 or 2012. They're brand new. Okay? There's several more coming in this year, at least, in 2014. So it's very new. It's not as mature as Python is in the community. It's complementary to Python. It is far more statistics and more authoritative statistics. It's the place to go jamming on your saxophone. You don't want to do jam in Python. You want to jam in R. But maybe you'll then take your results, your final methods, and maybe do it in Python. Calling R as needed. Wouldn't surprise me if that's an excellent way for us to operate. Okay. Will you please, I'm sorry, give me a moment to get settled here. I spent my time not in practical ways. So give me a couple minutes to organize myself, and then we'll start the last of my R tutorials.
Before you continue, so did you try doing the wireless thing with the... Did you get that email from them?
Yes, but I don't need it.
I don't know if this works.
Yeah, I'm good. Thank you. Okay, this is a shorter presentation, less complex. I think it's not quite as widely applicable as clustering, classification, and regression. Nonetheless, it's of interest to some of us, and maybe you'll enjoy it. I have no idea. I'm going to give a few slides called spatial point processes. It's a specialized field of statistics. And then we're going to move to a R script called 6_spatial processes.r.txt, which is on the same web page as the others that you've seen. Okay, let's give a brief talk of a somewhat smaller field on what do you do with points in a low-dimensional space. 2 or 3 dimensions is typical, although the methods may not be mathematically restricted to that. So this is an interesting point. It's actually points in P space, endpoints in P space, n cross P, type tables that I just talked about. We just call that multivariate data sets. And we now did multivariate analysis and multivariate regression and multivariate classification. And actually, this is sort of the same thing. It's just P is 2 or 3. So why bother calling it a different field? And actually, we really shouldn't. But it ends up that spatial, if you think of them as X, Y, Z coordinates, it sort of just has a different group of people, different groups of mathematicians did it, often associated with the earth sciences. Map people in geography and geology and in agriculture, in forestry. That's where this field sort of came from. And some of it has links to multivariate methods that we talked about, but some of it sort of has a different feel. So I wanted to give you a sense of this other field. Okay? So here it is. If you wanted to give a quick name to it, let's call it geostatistics. But it's really a group of issues. Okay? So in astronomy, spatial point processes naturally arise when you have 2-dimensional distributions of something in the sky, RA and DEC. By the way, it's a sphere. You do it at large scales, but it's a plane if it's small scale. And the third dimension, of course, is the depth dimension, which is very difficult in astronomy. We have parallax for nearby stars. We have redshifts for approximate distances for galaxies. But it's not easy at all for us to get the third dimension. But it really can be applied to any low-dimensional parameter space. It doesn't have to be spatial. The kind of problems that we have tend to be fairly challenging, particularly something like galaxy clustering. So galaxy clustering is not, here's a cluster and then there's nothing, and then here's another cluster. And then you can separate them and do, let's say, cluster analysis. We tend to get these hierarchical, elongated filamentary, soap bubble, anisotropic type clustering. It's really quite complex. The origins, of course, of large-scale structure was here at Harvard with Hooker and Geller and others in the 1970s and 80s. And this is a very challenging problem. I have brought this data set of galaxy clustering to the leading, not all of them, but to a couple of the leading spatial point processing statisticians, and they don't like the problem. It's quite difficult. You'd have to give them millions of dollars for years, okay, for them to do a good job, to tell us something new. It's not easy. Okay, but any field has jargon, and jargon actually can be meaningful. It has concepts, okay? So let me give you some concepts. Actually, some of these concepts, well, I won't say that. Stationarity means that the process, whatever the process properties are, it's invariant under spatial translation and maybe spatial rotations, so that we would call that isotropy, okay? So that the structure of, let's say, galaxies or whatever in the sky, it doesn't depend on where we look. If it's a dots, and then dots are not so common that they become Gaussian, it's called a Poisson process. So we have Poisson spatial processes. There's also Poisson temporal processes in time series. There's a little bit of jargon called CSR, complete spatial randomness. This means that, let's just say in 2 dimensions, I take a piece of white paper, I take some pepper, I close my eyes and shake the pepper shaker over it. It's completely random. That's a completely spatially random process. And unfortunately, they have too many methods for that because it's a stationary Poisson process. Because almost everything of interest to us is so non-stationary that we're nowhere near CSR. Okay, we don't have to say, oh, I wonder if it's really close to being random. I mean, look, it ain't random. These are real structures in the universe. And that. Now, here's another piece of jargon you should know about. It's called a marked variable. Yes, there's some stars or galaxies or clouds or sort of locations in the sky of interest, spatial locations, but I'm measuring something about them. I'm measuring the mass of the object or the color of the object or the star formation efficiency of the or the velocity structure of the object. So I can have many secondary variables associated with a point process. It's very interesting. So let me tell you an analogy. A company, think of Exxon Mobil, wants to find something called oil, okay? And they go and they hire some geologist to dig a well and then go down or maybe do seismology and find over here where the shale layer is that might have oil. And then they dig over here and they dig over here and over there and they get an irregular sample. And they say, oh, the shale layer is 4,000 feet here and 7,000 feet here and it is something else. But they know the shale is continuous and they want to map the continuous surface from an irregular point process. So that's actually a regression problem. Okay, that was the solution to that used by geostatistics is the marked variable is the depth to the shale layer. For us, the marked variable is, I gave it one of them in my talk yesterday. The marked variable in that case was a binary variable of whether a young star has a disk or doesn't have a disk, called a disk fraction. Okay? So it could be a binary variable, it could be a categorical variable, or it could be a real number variable, a marked variable. And it could be many marked variables, all in a spatial context. So for any stationary process, you can have global statistics, and that's often what's done, even though it's often not stationary. But you can do spatial autocorrelation, and that's very interesting. It's like the autocorrelation function of a time series. We'll get a look at that in a minute. And spatial clustering to find lumps and bumps. And you can find them statistically globally, or you can actually go around and try to find them individually. And astronomers do both of that type of approach. If you have an inhomogeneous process, and we often do, there's a lump and the densities are higher and then there's lower and things are inhomogeneous, then you just want to map it. You just want to interpolate it. You want to regress it, local regressions, either the distribution of the objects or the distributions of some marked variables. And then you can try to model it. Modeling means, of course, you have a formula. Maybe it's a polynomial model. Maybe it's an astrophysical model, perhaps. Maybe it's an NFW, Navarro-Franken-White distribution of dark matter, or something like that. Okay, so if you have a spatial model, then you can either have deterministic spatial models where you just do regression, or stochastic models where you judge the whole thing, they occur in random places and stuff, but there's still an analytic model underneath. And it can be involving the spatial intensity, the marked variables, or maybe a temporal thing. It can be quite complicated. And this is quite advanced. This is the more advanced, mathematically advanced area of spatial analysis, involving Markov random fields and Gaussian fields and things like this. So things like the CMB, cosmic microwave background modeling, using lambda CDM models, it is essentially astronomers and astrophysicists doing spatial modeling of in that case, not a point process, but a spatially continuous, pixelated variable. Okay, so each chapter of our book, I'm not trying to promote the book so much, but each field, regression, classification, density estimation, spatial point process, has jargon, concepts, and associated jargon. And we may have some intuitive understanding ahead of time of some of it, but it really helps to know their way of phrasing it, to hear it from them, and to learn their jargon. Until you learn their jargon, you can't read their books. You can't even read Wikipedia. You have to learn something from them because they're the ones who developed the mathematics and the tools. Okay, so now let's get into some tools. You'll be seeing this in a few minutes in R. In the 1950s, Moran's I and Gary's G are very simple, sort of very spatial, sort of on different spatial scales. They're actually bin statistics. We're very familiar with Moran's I type way of thing. You bin the data, you count up, you look at the variances, and you make plots of that called variograms or parallelograms. It's sort of like a linear correlation coefficients in the spatial domain. It tells you autocorrelation between bins of different spatial scales. And it's just a nice thing for stationary processes to characterize sort of what scales the structures are. You might think of wavelet transforms as a very fancy version of this. On different scales, it sort of highlights the structure at different scales. This is not a full wavelet transform. It's sort of more of a one-dimensional version than a two-dimensional version. Then there's tools associated with spatial interpolation. You have these irregular samples of shale layers, and you want to map the shale layers to drill for oil. So you use kernel density estimators, or you use KNN non-parametric estimators, or you do IDW, which is one that's developed by geographers, or you do Kriging, and this is the one that is closely related to Gaussian processes. It's actually just a local least squares regression, very similar to what I described in local regression on Wednesday, but it's done in a spatial context. That one works for marked variables, and these are commonly used. There are entire books on these things, on spatial interpolation methods. The most common is this Kriging. By the way, the reason Kriging has such a weird name is named after Mr. Krieg, a South African mining engineer of the 1960s. And Kriging was brought into geostatistics by Professor Journel and Marcheron, I forgot, the two French petroleum engineers who went around and gave seminars just like I am to all the geologists of the world for 20, 30 years. They gave these seminars and got Kriging. And then the statisticians sort of woke up and found, oh, it's just least squares local regression, and had a lot of statistics behind it. It was perfectly good. Kriging is great. We should be Kriging when we need to do interpolations of marked variables from irregular point processes. It's not often we do it, but once in a while we do. Okay, some of you may have heard of the two-point correlation function. Some of you have heard the greatest originator of it, P.J.E. Peebles, the great cosmologist of our time. My time, at least. I guess he's retired now. Okay, it ends up, you say, well, thank you very much. You're going to tell me about second-order moment measures. You're certainly going to tell me about the two-point correlation function, aren't you? And you look it up in the index of the book, and it's not there. There's one textbook, a good one, 2008 textbook, which has like 5 pages. It says, oh, by the way, the astronomers use the two-point correlation function, but we're not going to talk about it. Okay, why not? Wait till 3 o'clock. The reason why not is that they don't like the binning needed, the radial binning of the two. They do an unbinned cumulative distribution. They do the integral of the two-point correlation function. It's called Ripley's K. Brian Ripley, distinguished professor of statistics at Oxford, did this when he was a young man in the 70s or 80s. Okay? So it ends up they do Ripley's K. But Ripley's K is related to G distribution, which is distribution of nearest neighbor distances from the data points. The F distribution of nearest neighbor distances from random locations, which we might be called something related to the void distribution function. Ripley's K, the average number of points within a distance D of data points, the integral of the two-point correlation function. And since that one actually goes up like a parabola for a random process, you just divide by distance squared and you get L. BSAG's L star function is just the same thing that's variance stabilized. And then Baddeley invented a certain arithmetic ratio of G and F that all of these things have strong dependence on the shape and the edge. When you get near the edge of a point process, your statistics are always isotropic, and you go over the edge. So this particular Baddeley's J by Leishot and Baddeley have reduced edge effects. And so it's really bizarre. We have Peebles leading to a field of 2-point and 3-point correlation functions and a lot of mathematics developed by astronomy. And everyone else, all the geosciences, earth sciences, and all the mathematicians are sitting over there with Ripley's K and doing mathematics over there. There's a lot of parallels. I think a lot of wasted time by somebody for doing it twice. Okay, but it's not always the same. And I think some of the statisticians should go look and see whether we've done some interesting stuff mathematically. I don't know. A lot of them, if you have CSR, so complete spatial randomness, they have asymptotically well-defined probability distributions through the central limit theorem, and you can get probabilities. But in more general cases, you have to bootstrap the data. But the bootstrap doesn't work for all the correlated phenomena. You got to do the block bootstrap. Oh, it goes on and on like this. Okay, it can be quite complex to fully analyze a data set. Well, that seems to be my brief lecture on spatial point processes. Let's go and take a look at them in R, and then we'll open the floor up to any comments or discussions. So in this case, I hope my web works. Let's see if it does. We're going to read a small data set of galaxy redshifts. This happens to be from something called the Shapley concentration. Shapley, another Harvard astronomer. I can't, you come to Harvard, and I got all the way back to the 1850s and all the way up to the present. It's a pleasure. To Hooker and Geller, it's a pleasure to be here indeed. So this is just some standard stuff. I've done this before. I attached my little input file so I can use the names of it. I asked the dimensions. It happens to be 3,996 rows with 5 columns. I asked for a summary of the columns. It ends up I have RA and DEC. Notice they're not full sky. They're in a few degrees of the sky. I have magnitudes, which is a mark variable. I have velocities, another mark variable, and I have the error bars on the velocities, which, by the way, the methods don't use. Vinay and others have said, well, can you use my heteroscedastic measurement errors? And you go look in the books on spatial point processes? No. Why? Because foresters don't have measurement errors, and that's who they developed the methods for. Oh, I hate this. I hate this. I really hate this. Okay, I'm just going to make some subsamples, a high density part of it, a low density, a very high density version of it, just for my own use for the book. So let's now look a little bit of graphics. There's one of the major, I'm going to get it wrong, OpenGL is a graphical interface. What's OpenGL? It's a graphical language. It's a language, a graphics language. And it's open. So I'm going to bring in R's version of OpenGL called RGL, ridiculously. In this case, it's 4 megabytes of R. It's one of the larger packages we're going to be using in this seminar. So I'm going to wait a minute here as it brings it in. And this is also, someone asked, do we have interactive plotting? And I said, well, yes, there's an advanced CRAM package called iPlots. And this is one of the ones that is an interactive plotting package that I'm just going to show you because it's very respected. People like RGL in the R world for low-dimensional visualizations. So because I have, with RA, DEC, and velocity, we have 3 dimensions, 3 spatial dimensions, if you think velocity is just a Hubble flow. And so let's take a look at our data set in 3 dimensions. Okay, thank you. I've downloaded my file. This particular one has its own little language. You got to do the help files to find them. I'm going to do RGL open. And it's opening up its own special little device that's different than the usual plotting device. I'm going to put RGL points. I'm going to put my points on for one of my subsamples of galaxies. Ta-da! I'm going to put a box around it. Ta-da! And that looks like a mess. But like I said, it's interactive. I'm going to take my cursor and I'm going to run around. Oh, look at that. I can project it a little bit. It does some shading for me. Oh, yeah, there's some structure. There's some structure indeed. Okay, RA deck and velocity. It's not that hard for me to find the cluster in this mess. So I actually have multiple velocity structures in here, and they're flattened. They're not isotropic. I can take a snapshot of that version of it and put it onto my disk. I just did that. Shapley.png. This particular program does PNGs instead of EPSs. I don't know why. It was written by somebody. And I'm just going to close my RGL window. Close the window. Oh, well. I'll close the window. So that was one way of plotting 3D things. That was more dynamic. Here's another way of doing it. How about just using the plot command? It normally makes two-dimensional plots. But why don't I scale the size of the symbol to the third dimension? That one happens to be the unclustered part of the data set. So you can take a look. I think one time I made my PCH depend on a variable. That was the symbol type. In this case, I made CEX dependent on a variable, the symbol size. And notice I normalized it. Use scale to bring it into a reasonable scale. I can also use, someone wrote a CRAN package, not a particularly sophisticated one, called Scatterplot 3D. That's actually designed for 3D scatterplots, but not interactively so. And this one does a perfectly reasonable job of making 3D scatterplots for publication. There it is. It's static. Can't move it around. But there it is. RA deck velocity. I could publish this in the AppJ if I wanted to. So that was very quickly 3 data visualization tools. We didn't do much data visualization here. We're going to do a second edition in a year or so that will have a whole new chapter. Because data visualization is actually an entire field of computer science, really. And it's actually combined with human psychology and human vision. And there's color schemes, and there's ways of displaying things. There's alpha blending, which sort of means translucency, to see through parts of what you're doing. And you all know this. Computer visualization is extremely important in Hollywood and television, and all the beautiful images that you see in the commercial world are developed using insights from computer science and psychologists working together to make data visualization important, or visualization important, and for us, data visualization. So it's a whole field that astronomers are actually not particularly knowledgeable about most of the time. Okay, I'm going to take you through little tiny portions of several large packages that do spatial point processes, most of them developed for the earth sciences. The first one is called SPADIP, spatial dependence. Oh, this one I saw used for census data, economic census data. This is the example I saw. And they were, I don't know, asking questions about poverty for counties in Georgia or something like that. It was something sociological. And actually, the presentation I saw was by a postdoctoral scholar at Penn State in the social sciences. It was quite elaborate, quite sophisticated. I was impressed. I didn't think it had much to do with astronomy, that particular one. But I found something that I thought was interesting. And in this particular case, I had to learn to set up several. I had to do a KNN, nearest neighbor sort of analysis ahead of time, and then I ran a couple programs, and then from that I was able to do Moran's I, which is one of those global statistics, and Moran's I has a value of 0.95 for this particular data set. Thank you. So what? Well, I can do a statistical test against complete spatial randomness for that. And the answer is the value was 0.95. The expected value was 0.007. The probability is less than 10 to the minus 16. Boy, that was significant. Like I said, we're not often interested in these rather simplistic hypothesis tests against randomness. Now, this is not a very sophisticated algorithm. A statistic. Moran's eye is just a question of variances. It's a 1940s procedure. Other ones we might get to are more sophisticated. Okay, so this one included a Monte Carlo simulation. These are quite sophisticated packages, even though that particular computation may not have been particularly much. And here's Geary's C, which is another similar statistic. I'm now going to bring in one of the geology packages. This one's called GStat. Geology statistics or something like that. And now I'm going to show you something they do a lot and we don't do. I'm not really sure it's that valuable, but it's a maximum likelihood variogram. It's sort of like Moran's eye in that it's telling you how much autocorrelation there is at different characteristic distances. It's not silly to ask that question for astronomical data sets. It will say, oh, well, things are more important around, 3 kiloparsecs or megaparsecs or whatever than 10 megaparsecs. Oops. That's interesting. That means my plot's going to fail too. Sorry. So this particular one is going to fail. We'll see if I can avoid problems on the next one. This one also is going to do a variogram analysis. Our favorite is called SpatStat. As you can see, it's 10 megabytes in size. It's huge. Adrian Padley in Australia, a statistician who does pay attention to astronomers. He is on the organizing committee of the Lisbon meeting on statistical challenges in cosmology coming up. And he's a collaborator of my research group as well. And he wrote this very large package that basically does enormous amounts of spatial statistics. Wonder if I personally can avoid doing this. You may have to bring it in. Let's just see. I may already have it. See whether I've got it here. Okay, I think I have it, but you may have to wait a bit. There's so many of you loading on the same. Oh, actually, you're at a different network. You may be fine. Okay, I'm bringing in SpatStat. Once again, these are very complex software multifaceted products. You have to read the manuals. In this case, you have to set up a window. It finds out the size and the shape of the survey that is being made. This is the centroid and the area of the windows. You have to set up special, I think they're called R classes. He calls it PPP class. Special structures using his special software. This one is called planar point patterns. And let's do a summary on that and see what it produced. It has 142 points with an average intensity of 10 points per square unit. It is has marked variables that are numerical, that are integer, has a minimum, a maximum, and a median, and has the following rectangular window of this area. Okay, thank you very much. That's sort of infrastructure. Let me take a look at the actual data that you think is there. Well, here's a smooth version of this data set, and here are the underlying points. And in this case, again, the circle size is scaled to the third dimension, which is velocity in this case. So we're doing a smoothing of the density and a plotting of the two-dimensional density and a plotting of the third dimension in this particular plot. I personally don't think this particular plot's telling us much about galaxies in the Shapley region, but it's not sort of the end of things. So let's now see what we have here. This is the K estimator, Ripley's K. It did that in the blink of an eye. Here it is for with different corrections for the edge effects. Here are some plots of Ripley's K as a function of distance and degrees. This is the integral of the two-point correlation function. The solid line is the data. The dashed line is random, I believe. And I'm trying to remember what the dashed line is. I thought it was, legend equals false. Well, maybe if I did it with legend equals true, I would actually learn something. There's a legend. Uncorrected. I think uncorrected means it's uncorrected for the edge effect, and the other one is some sort of a correction. I need to read the help file to find out what it is. Okay. So now in this case, I'm going to draw an envelope of 100 simulations around the one that is the assumption of no effect at all. It's just a parabola. It's just a pure parabola of random. And this particular is a very small data set. It didn't significantly deviate until I got out to 0.4 degrees. Obviously, the deviations are stronger in larger data sets than this. So there is a fair amount of simulation capabilities in many of these spatial statistics packages. Baddeley's J is the one that is more sensitive. Once again, the dashed curves represent different edge correction algorithms. This is a function of distance again. This negative, in this case, going below 1 means it's clustered. The flat line, in this case, is complete spatial randomness. And just because we want to see it, there actually is a two-point correlation function. They call it the pair correlation function for the same data set. And that, by the way, is the pair correlation function from the literature. Basically, gamma equals minus 1.8 to show that we can reproduce. It's what we expect. It's the galaxy distribution. It's a very small sample. So we only got it out to to a small distance. There's no BAO signal in this very small sample, but in principle there is. So it does sort of what we're used to at the same time, but most of the code is devoted to things that we're not used to, such as Baddeley's J. Here is a Voronoi tessellation. It's a mathematical construct from graph theory. It's pure math, based on the Dirichlet tessellation. That's almost the same information. Is the same information. This is actually done by some astronomers, and there's nothing wrong with it. In fact, it's quite nice sometimes, and it's quite useful for certain purposes. So in this case, I just told you what's inside of that file. So in this case, I said, okay, let me do something with my Voronoi tessellation. Let me say whenever I have a whole bunch of small tessellates that are together, I'm going to sort of mark them specially, and maybe I'll call that a cluster if I choose to. I have to make up a threshold to do that, but let me try it. So there we go. There's a tessellate, and those are the ones with circles represent the ones that are small tessellates, small tiles, and then I also put the dots in for every tile. So there's sort of more clustering here, maybe 2 clusters here, and it depends if I want to call those clusters or not. That's up to me. if I think they're interesting scientifically. Now, I've mentioned kriging as this important, essentially least squares regression method, local regression method. And so I'm going to go to one of the other geostatistical packages, just to sort of give you a sense of the diversity, and each of them is different. All of them have books associated with them. They're widely used by earth scientists and geologists. This is a series of diagnostic plots that comes out for the Shapley data set of different characteristics of the data, both plotting it in raw ways and smoothing them a bit. But this is let's see, the last time I tried this, it failed. Let me see in this package if I can get it done. This is a variogram analysis, making a plot that we don't see much, but they talk about a lot in geostatistics. This is sort of the small scale noise. It's called the nugget effect, and this is the range as a function of distance in, I guess, degrees. And that's the amount of correlation, spatial autocorrelation. And then they fit this with analytical models. So this is sort of a stochastic. They're not finding clusters. They're fitting the overall global behavior of the clustering in this particular univariate fashion. So that dashed line represents a Gaussian fit. And it ends up that particular fit is needed as a sort of an input into the kriging algorithm. And so now we're doing a Krieg calculation, and it's actually, my computer is busy computing right now. Chunk, 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 even though there's only hundreds of points. No, there may be thousands of points here. This is a fairly elaborate calculation. It's just a least squares local regression, but it is called kriging, and it is doing it. There's many versions of kriging. There's universal kriging and co-kriging, and it just goes on and on. There's books on this, and some of them are probably fairly useful. Again, you have to read the manuals. In some cases, you even have to read the books to use these methods in a wise fashion. But I actually did this, rather my student did it, showed in my lecture that I gave yesterday, in a really useful way. We ended up mapping the disk fraction distribution across star-forming regions. In this case, we're going to map a sort of a silly quantity. We're going to map the average velocity as a function of RA and DAC. And the reason it's sort of silly in this case is that this clusters behind clusters have nothing to do with each other, and the average of them is not very interesting. But nonetheless, it does it. And the important thing is that it not only does the smoothing, that's not that hard, but it gives the variogram. It gives the variance, the uncertainty in spatial map. It gives the uncertainty of the map that you just made. And that really is something that is nice and useful and powerful, so that you know not only, oh, that's where my interesting structure and my marked variables are, but that's where I can believe it's a good measurement, and that's so in another place I find it's not a believable measurement. And my computer is actually computing. There we go. I finally finished. Thank you very much. And now I can plot the output of it. And it is a map. It is maps. I happen to put the dots on top of the map. So the colors here represent high and low velocities. And the map here means high and low reliability. In this case, darker color means I have a lot of good data and it's very reliable. And a lighter color here means I don't have much data there, don't really believe it, and why can't I forget it? I don't have any knowledge. So you say, oh, look, I've got a very, very unusual value of my velocity. But ladies and gentlemen, it's in a part of the map when you have no data. So just don't believe that. So that's just an extrapolation, essentially, that's unreliable. And anything right here is unreliable. But that yellow, that one over there is very reliable. That white there is very reliable, okay, because it has a good reliability indicated on the semi-variogram. So they have this jargon, variograms, semi-variograms, covariances. It's a little world developed by geologists for themselves. Statisticians are involved. Ripley, for instance, is a statistician. Krieg was not a statistician, but his work has been refounded in statistical terms, so it really is applied statistics. And these tools are very commonly used by earth scientists and ecologists and biologists, and there's perhaps sometimes these tools are useful for astronomers. But since astronomers didn't know about them, we thought, hey, this is one of the many fields to bring to your attention. There's another chapter in the book of a field of treatments of upper limits, of non-detections. It's not a perfect treatment. It doesn't take into account that the upper limit itself is sort of stochastically known, not perfectly known. But nonetheless, the field is called survival analysis. It was developed for quality control industry and for pharmaceutical industry, for biomedical experiments. Let me give you an example. You have 100 rats. You give them a disease. Name a disease. Diabetes. Okay. 50 of the rats, you let them have diabetes, and 50 of them you inject with a new possible drug that might help cure diabetes. And then you wait for the rats to die of diabetes. So the rats who have diabetes tend to die faster. Their survival curve is sort of shorter. The ones with the drug hopefully live longer. But some rats live for years, and you get really tired of waiting for the last one to die so you can get the mean survival. So you stop the experiment after a while, and you have these lower limits to the survival time. And therefore, you have to adjudicate what's the mean and the differences, the two sample tests. Did the drug significantly improve the longevity of the rats? That problem and similar problems of building widgets of different characteristics in factories, quality control, manufacturing quality control, where longevity is how long does the widget work? What's the lifetime of your light bulb? That problem, and you don't want to wait for all the light bulbs to die, okay, because you're just impatient, led to an entire field of mathematics called survival analysis. It's reasonably good. It's not that difficult to understand. It has, theorems. It has variances. It has, asymptotic normalities. It has all sorts of nice statistics behind it in methodology. And so, I'm an educator mostly, but this is the only thing I ever did in astrostatistics. Okay, I translated longevity of rats into quasar luminosities. I then turned survival of rats, which was a lower limit to their survival, I multiplied by -1, into an upper limit to the quasar luminosities, which are sometimes undetected. So we have some measured quasar luminosities, some upper limits to quasar luminosities. We want to know the mean value or the regression or the two sample tests or all sorts of things we might want to know about quasar luminosities in the presence of upper limits. All I did was take the mathematics available from 1970s, 1980s, most 1960s, 70s, and 80s. There's a relatively recent field of applied statistics, of survival analysis, applied it to quasar luminosities, multiplied by -1, and got the answer back. And that was my achievement. Astrophysical Journal, 1985 and 86, with me and a statistician who taught the class. I took the class in that. It was an extremely boring class because all he cared about were the theorems. It was a graduate class for statisticians. I don't care about the theorems, so I slept through the class and we wrote 2 abstract papers, the best work I ever did in my life. 1,000 citations. I influenced astronomy quality of analysis with upper limits. Frankly, we were doing a lot of crappy stuff before that. Okay? So this is my only achievement personally in astrostatistics was to multiply by -1 and change longevity into luminosity. And that means I'm not a very sophisticated astrostatistician. There are other people in this room who are much better at it. Vinay is going to tell us some research results from Harvard's cross-disciplinary group that really represent real innovations in methodology. In fact, he may even talk about non-detections. So this is an example then of spatial point processes, of most of the work being done for the geosciences, the earth sciences, and ecology. And some of it may be useful to us. So we don't have to, but we can read books. And my book is mostly an entree into these fields. Quickly summarizes some of them, gives you a page of recommended readings of things to learn more, and gives you this particular script here to just exemplify some of the capabilities of these codes. The codes, I would say the codes are 50 times bigger than what I'm showing you here. And that's just a few CRAN packages. So they're big. They're serving entire research communities and industrial communities of geosciences and ecologists. So, ladies and gentlemen, I'm finished with my last practical lecture. We have a few minutes before 11:30. Does anyone have any questions or comments? Sir.
You mentioned, I don't know if you're aware of this, but your book's actually available for free online through the Harvard Library website.
I had no idea.
Yeah, so it is.
Is it legal?
Yeah.
Oh, great. Fabulous.
Yeah.
Oh,
Harvard Library paid it and you can get it online.
That's wonderful. 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 Great. Fabulous. I didn't know that at all. Anyone else? I think we're all free then. Finish the cookies and back. I don't know who eats the cookies that are left over. I'll turn the floor back to Vinay Kashyap.
Hi, thank you, Eric. So we are done for the morning session. We'll be back here at 1:30, where I will be, I don't know how this happened, but I'm pinch hitting for you for an hour, talking about Bayesian Poisson processes, an introduction to Bayesian analysis and upper limits. If you saw Frank Primine's email, this is basically the background to that paper. And following that, Eric will be talking about common mistakes that astronomers make. I'm sure he will need another day to go through all of it, but he has to leave for the airport, so he'll probably finish in about an hour. Once again, so thank you all for coming, and thank you again, Eric, for doing this. And I should also thank Sean Gallagher up there, who is manning the videos, and Michelle, without whom you would not have these cookies, actually. So thank you all. And I'll see you at 1:30 then.